Let's now see what exactly is the problem with the page tables that we just saw. This kind of page tables are also called one-level page table. And for the parameters that we had in the previous video, the size of the page table was coming out to be 3 megabytes. Well, 3 megabytes out of 1 gigabyte is not really much. So where is the problem? This 3 megabyte we need to pay for each application that we want to run on the system. Let's say we are running 100 applications concurrently. That means 300 megabytes of storage is used only for page tables. So if we have a memory of 1 gigabyte and we are using 300 megabytes only for page tables, we are losing 1/3 of our total memory capacity, which is huge. And this is especially important because not all applications make use of this 3 megabyte. This 3 megabyte is used when your application is using whole 4 gigabytes of virtual address space. If the application is using less, even though this space is reserved for the page table, this goes unused. We never used it. We never use it. We never map any page to that space. And the main problem here is that in one level page table, you reserve the space for all possible virtual pages up front. When you start executing application, you just say, hey, I may have these many virtual pages, so reserve me this much space so that I can translate them. And if you are not using that space, you are just wasting that space. And this is especially important because there are lots of applications that do not need 4 gigabytes of storage. Consider about your text files or maybe even small music files. They are maybe in kilobytes, some of them may be in few megabytes, but not in gigabytes. So for all of these applications, we are reserving these 3 megabytes, but we are only using a fraction of it. And if most of our applications are of this kind, we are wasting roughly 1/3 of our memory capacity in not doing anything useful. So let's see what we can do about it. Well, we can go to multi-level page tables. What a multi-level page table is that you have multiple levels of page tables. Here we see 2 levels. The last level really holds the pointer to the pages. So it's the last level that tells what exactly the physical page number is. The other levels, they point to just their immediately next level. So in this case, the first level is pointing to the tables in the second level, and the second level tables are really telling us what exactly the page number is. The advantage in this case is we need to reserve only space for the first level page table and maybe one of the second level table. The remaining tables at the second or subsequent levels will be allocated on demand only when we need them. So if we need that space, if we use that virtual address space, only then we insert a table that will hold the translation for that portion of the virtual address space. Otherwise, we do not add that table. So we don't use that capacity. So now the question is, this technique would be useful only if the individual tables are smaller than what we had in the first level table, in the one level page table scenario. Let's see exactly how big these tables are. So here is our same example. We have 32 bits of virtual address space. And let's say out of these 32 bits, 12 bits are for page offset, and the remaining 20 bits are for virtual page number. So since we have 2 levels of page tables, we divide our virtual address, the higher bits of our virtual address, into 2 parts. In this case, we divide them into 10 bits and 10 bits. These 10 bits take us to the first level, and the second 10 bits take us to the second level of tables. Now with 10 bits, we can have 1K entries in this table. And we know each entry is only 3 bytes. So each table is only 3 kilobytes. Now let's see how many tables we need for our application. So let's say we want to cover the full address space. We have an application that makes use of all 4 gigabytes of data. In that case, all of our entries in this table will be used. That means we will have 1024 tables at second level and 1 table at first level. So in total, we have 1025 tables. If each table is 3 kilobytes, we get slightly more storage than 3 megabytes. So if an application is making use of its entire virtual address space, we end up paying 3 kilobyte extra storage if we have two level page tables. Well, okay, we are losing 3 kilobytes because we have one additional table at first level. But let's see, for majority of applications that do not use the full address space, how much do we pay in page table cost then? So let's say we want to cover only 4 megabytes of address space. This is enough for a lot of application, if not most. So if you look at it, so here we have hexadecimal digits. Each digit correspond to 4 binary digits. So look at here, this is the smallest address and this is the biggest address. So top 10 bits are never changing. They are always 0 here and here. That means these bits are always 0. So you will always go to the only first entry, and this entry will take you to one of the second level tables. So we need only 2 tables in this case, because with the higher 10 bits, we always go to the same entry in the first level table. So we will always go only to one table at the second level as well. We just have 2 tables. Each table is only 3 kilobytes. So in total, you need 6 kilobytes of storage. So we have reduced from 3 megabytes of storage to only 6 kilobytes if our application fits in 4 megabytes. Let's see what happens when our requirements grow. So here we go to 2 gigabytes, which is half of our 4 gigabytes total virtual address space. In this case, only the most significant bit remains 0, whereas all other bits change. That means we will use half of the entries in our first level table, and we will have 512 tables at the second level, since only half of these entries will be used. So we have in total 513 tables. Each table is 3 kilobytes. So we end up paying 1.5 megabytes, which is half of what we had in a single level table. But we are paying this 1.5 megabyte when we are sure that we will use 2 megabytes of virtual address space. So the good thing about 2 level page table is that our storage requirements grow only if we are really using more virtual address space. If we are using less virtual address space, we pay less in storage. As our requirements grow, our cost grow. So the cost is proportional to the uses, whereas in the single level page tables, the cost was always fixed irrespective of how much exactly we use. So for applications that have only small virtual address space requirements, we gain a lot by going from 1 level page table to 2 levels of page tables. Let's now see how exactly address translation happens with 2 level page table. So we have 2 levels of page tables. The tables at first level points to tables at the second level. And this is how we divide our addresses into byte offset and virtual page numbers. Byte offset doesn't really change, or page offset doesn't really change. Then our page table base address, it points to the beginning of the first table. So to select an entry from the first table, we take that address, add it to the upper 10 bits of the virtual address, and we go to one of the entries. Then that entry takes us to the beginning of one of the second level tables. We add that to the next 10 bits from our virtual address, and we go to one of the entries in the second level page table, which gives us the physical page number. So we have 2 hops here. First, we need to access memory to get an entry from this table. Then we need to access memory to get an entry from the second table.